The night sky, once a canvas of twinkling stars, is now increasingly populated by moving points of light, satellites. As of May 2025, approximately 11,700 active satellites orbit our planet, a number that has more than doubled in the past 5 years. This surge is primarily driven by private companies like SpaceX, whose Starlink constellation alone accounts for over 60% of these satellites. But as we continue to launch more satellites, we must ask, how many satellites can Earth's orbit accommodate before it becomes dangerously overcrowded? The low Earth orbit, or LEO, extends from about 160 kilometers to 2,000 kilometers above Earth's surface. This orbital band is the most crowded, primarily due to its convenience for Earth observation, communications, and scientific missions. Its proximity allows for reduced latency and quicker data transmission, making it especially attractive to commercial satellite operators. However, this convenience comes with a cost. With each new launch, the margin for error grows thinner. Researchers, including Jonathan McDowell from the Harvard and Smithsonian Center for Astrophysics, have been tracking satellite launches and raising concerns about orbital capacity. Studies suggest that the carrying capacity for LEO could extend up to 100,000 active satellites. Beyond this point, the risk of collisions increases significantly, potentially leading to a cascade of debris known as the Kessler syndrome. The Kessler syndrome describes a scenario where the density of objects in LEO is high enough that collisions between objects could cause a cascade effect, each collision generating space debris that increases the likelihood of further collisions. This chain reaction could render certain orbital regions unusable for generations. The theory was first proposed by NASA scientist Donald J. Kessler in 1978. He warned that even a single collision in space could trigger a catastrophic chain of debris-generating impacts. The more crowded our orbital highways become, the higher the chance that a solitary accident spirals into a cascade that could take out dozens, if not hundreds, of functioning satellites in minutes. And once set in motion, it could take decades or even centuries for Earth's atmosphere to naturally clear the clutter. To mitigate these risks, companies like SpaceX have implemented autonomous collision avoidance systems. Between December 2020 and November 2022, Starlink satellites performed over 26,000 orbital avoidance maneuvers. Satellite operators now rely on advanced algorithms and real-time data to detect possible collisions up to a week in advance. Some systems even allow satellites to autonomously maneuver out of harm's way without human intervention. But this automation introduces new complexities. When two satellites both react to a predicted collision and alter their paths simultaneously, it can paradoxically increase the risk instead of lowering it. Coordination among operators is critical, but currently there is no global body enforcing that cooperation. Astronomers are also feeling the effects. The proliferation of satellites has led to increased light pollution, interfering with ground-based observations. Studies have shown that twilight observations are particularly affected, with the fraction of streaked images taken during twilight increasing from less than 0.5% in late 2019 to 18% in August 2021 due to satellites like Starlink. In fact, entire astronomical surveys have had to revise their observation strategies due to satellite interference. Some observatories now use software to predict satellite paths and schedule observations accordingly. The Vera C. Rubin Observatory, set to begin operations soon in Chile, is implementing mitigation protocols to filter out satellite trails. Yet even these advanced systems may not fully shield us from a future in which the stars become harder to study from the ground. Ground-based radio telescopes are also being disrupted by satellite transmissions. Astronomers studying cosmic microwave background radiation and faint signals from deep space are increasingly having to contend with broadband interference caused by satellite downlinks. These signals, while essential for providing internet to rural communities, complicate efforts to answer some of the most profound questions about the origin of the universe. Moreover, the environmental impact of re-entering satellites cannot be ignored. As satellites burn up upon re-entry, they release chemical components into the atmosphere, potentially contributing to atmospheric pollution and ozone depletion. Research into the atmospheric impact of satellite re-entries is still in its early stages, but initial findings are concerning. Each year, several tons of metallic compounds are deposited into the upper atmosphere from these disintegrating satellites. Scientists worry that over time, these compounds may alter atmospheric chemistry in unpredictable ways, especially if satellite numbers continue to multiply. To address these challenges, researchers are exploring various strategies, including better tracking of space debris, developing international regulations, and designing satellites with end-of-life disposal plans. The goal is to ensure the long-term sustainability of space activities. Currently, no centralized global authority controls satellite traffic in space. While national agencies like the FCC in the United States or the ITU in Geneva handle licensing and frequency allocations, there is no unified system for managing collision risks or orbital crowding. Experts warn that without stronger international cooperation and enforcement mechanisms, we risk treating Earth orbit like the Wild West, a frontier being rapidly filled with mettle and ambition, but little accountability. Over the past decade, the pace of satellite launches has accelerated dramatically. In the early 2000s, only a few dozen satellites were launched annually. Now, that number exceeds 100 launches per year, with many missions deploying multiple satellites at once. In 2023 alone, SpaceX conducted over 90 launches, many carrying Starlink payloads, contributing thousands of new satellites to orbit in just a few years. Other companies, including OneWeb, Amazon's Project Kuiper, and Chinese initiatives, are also deploying their own constellations. If satellite constellations proceed as planned, the number of orbiting objects could surpass 150,000 by the early 2030s. This number includes both active and inactive satellites, rocket stages, and fragments from previous collisions. At that scale, automated collision avoidance will need to become even more sophisticated, possibly leveraging AI to make real-time decisions across constellations. But can AI outpace the exponential growth of space debris, or will we reach a tipping point? Space surveillance networks such as the US Space Surveillance Network, SSN, currently track more than 30,000 pieces of orbital debris larger than 10 centimeters. However, hundreds of thousands of smaller, yet still potentially destructive pieces go untracked. Emerging technologies like ground-based phased array radars, optical telescopes, and even AI-driven pattern recognition are being developed to monitor these hidden threats. In parallel, private companies and research groups are designing space janitors, robotic spacecraft intended to capture and deorbit space junk. The growth of satellite networks is not just a technical issue, it's economic. Global satellite internet services are expected to generate tens of billions of dollars annually by the 2030s. Companies race to capture market share, but this gold rush into orbit may be prioritizing speed over safety. Insurance premiums for satellite launches are rising, and a single collision event involving a major constellation could cause billions in damage and decades of legal disputes. Some analysts warn that the lack of orbital governance could lead to a space-based financial crisis. As humanity's presence in space expands, so do the ethical dilemmas. Who is responsible for cleaning up abandoned satellites? Should there be a legal obligation to remove defunct spacecraft? Should developing nations be given equal access to orbital lanes? Or will mega-constellations monopolize the best slots? These are questions not just for engineers, but for lawmakers, ethicists, and society as a whole. The way we answer them will shape the next century of exploration. Space is not just a commercial or scientific domain, it's also strategic. Military satellites are used for surveillance, navigation, and communication. As civilian and military satellite populations grow, the margin for error narrows. A single misidentification or unintentional collision involving military assets could spark diplomatic tensions or worse. Many countries, including the United States, China, Russia, and India, have demonstrated anti-satellite capabilities, raising concerns about the weaponization of orbit. The blending of civilian and military infrastructure in LEO makes it harder to distinguish peaceful operations from strategic assets, further increasing the potential for misunderstanding in moments of crisis. When satellites reach the end of their operational life, not all are safely deorbited. Some are moved to designated orbital graveyards, hundreds of kilometers above geostationary orbit. Others, so-called zombie satellites, continue to drift uncontrolled, occasionally reactivating due to residual energy or system errors. These unresponsive objects pose a long-term hazard as they cannot coordinate with active traffic or avoidance systems. In the vastness of space, even inactive satellites continue to whisper the legacy of our outdated approaches to orbital traffic management. Around the world, innovative startups are rising to meet the orbital debris challenge. Companies like Astroscale and ClearSpace are designing satellites equipped with robotic arms, nets, harpoons, and other mechanisms to safely capture and remove debris. Other initiatives focus on in-orbit servicing, refueling or repairing satellites to extend their lifespan and reduce unnecessary launches. These early efforts may one day become a routine part of orbital maintenance, much like trash collection and vehicle servicing are on Earth. However, funding, cooperation, and legal clarity remain significant hurdles to turning prototypes into scalable, global solutions. The stars may seem distant and eternal, but the space between them is quickly becoming cluttered by human ambition. The sky is no longer empty, it's a growing archive of our digital lives, our scientific progress, and our unresolved conflicts. Only by approaching space with humility, foresight, and international cooperation can we ensure it remains a shared and accessible frontier. As we continue to explore and utilize space, it's imperative to balance technological advancement with responsible stewardship. The choices we make today will determine the future of our skies. If you found this exploration insightful, subscribe to our channel for more in-depth analyses on space and science topics. Join us as we continue to uncover the wonders and challenges of our universe.